Alrighty folks, so getting started here on chapter 2 of Physics 20 where we're going to start looking at vectors in 2 dimensions now. Okay, before we jump in, just a reminder, make sure as you're following along with the video lesson that you've got something to take notes with as you go. Whether you've printed out these notes and are filling in or are just following along on loose leaf, you want to be actively engaging because you'll get so much more out of the lesson that way. Okay, here we go. So what does it actually mean for a vector to be in 2 dimensions? Well, so far everything we've looked at has happened in 1 dimension, meaning essentially 1 axis, right? So maybe, a car was driving forwards but accelerating backwards, right? That was all just happening in 1 axis. It's not like it was moving forwards and up in the other axis there, right? So that's what we're going to start to look at today, because a lot of motion realistically does take place in more than just 1 dimension, more than just the x-axis or the y-axis. It often happens in both axes simultaneously. And so this is important when dealing with vectors where direction matters, right? If we're dealing with direction that's in more than 1 axis, well, we have to properly think about that and communicate it for vector quantities. Okay, so we'll see how as we go. We'll just remind ourselves, right, since we're thinking a lot about vectors and what that means, scalars versus vectors. So for scalar, they have a magnitude only, right? Magnitude meaning size, a number, right? But the direction makes no difference. Okay, so things like time, there's no direction for time, right? Mass, distance is a scalar quantity. It's just how far did you go, right? Not worried about direction. Speed, just the rate at which your distance is changing, or energy. All of those are scalar quantities. Today, we're mostly going to be focusing on vectors, and when we're talking about vectors, that's where we're going to have to consider 2 dimensions if applicable. Okay, so some vectors. Displacement, right? How far are you from where you started? And in which direction? Not just how far did you go, how far are you from where you started and in which direction, right? Velocity as opposed to speed. Velocity is the rate at which displacement is changing and in which direction, right? Acceleration, that's the rate at which velocity is changing. All of these are vectors. Force, we'll see that one a lot in Unit B, okay? So, just a reminder there of scalars versus vectors. For vectors, direction matters, and therefore we're going to have to think about some 2D stuff, as we'll do in this lesson. So as we've already seen, okay, but it's going to become much more important now as we start to do 2D stuff. Whenever we're adding vectors, the key is to draw your vector addition diagram, or VAD for short, okay? As well as something we're going to introduce today, the idea of a vector component triangle, okay? So if you've kind of been rolling your eyes at the diagrams and saying, come on, I could just do the math, okay? You're going to see why it was important to get comfortable with that skill in this lesson, because now the diagrams are going to become crucial. It's going to be almost impossible to get our bearings and solve these without some form of diagram, okay? So a quick reminder of the key parts of a good vector addition diagram, okay? We just represent our vectors as arrows, nice and simple, okay? If we have a displacement to the east, we draw a displacement to the east. That's how far we went east, okay? That could be a velocity, whatever. It depends what vectors we're adding. And then when we're adding up our vectors, we draw them tip to tail. And so all that means is at the tip of one, you start the tail of the next one. In other words, where that one stops, you start the next one. So maybe someone walked 5 meters east and then another 10 meters east. So that's what we mean by tip to tail, right? They walked 5 meters east, and then at the tip of that one, we start the tail, because afterwards, then they walked another 10 meters east. Now to find the resultant vector, which, like it sounds, is the result of all of those other individual vectors, right? You can think of it as the one vector that you would get from adding all of the other ones up, okay? To find that, we draw an arrow from the tail of the first, so where we started our diagram, to the tip of the last, so where we finished our vector addition diagram. Okay, so if this person walked 5 meters east, that's our first vector. Then they walked another 10 meters east, that's our second vector. To find their resultant displacement with a vector addition diagram, what we would do is say, okay, they started here. So from there to there is their total resultant displacement. That would be what we would call dr, the resultant displacement. And it's just the result of adding d1 to d2. Okay, we're going to go more complex with this today in 2 dimensions, but that's the basic idea always behind a vector addition diagram. Tip to tail to add them up, and then from where you started to where you finished to get the result. An important side note here before we continue, if we're going to add 2 or more vectors together, they do need to be the same kind of vector, right? Which makes sense. Like you can add a displacement to a displacement, or you could add a velocity to a velocity, but you can't really add a displacement to a velocity, right? For example, if I say, John walked 5 meters east, then ran at 1 meter per second to the east, it doesn't make sense to say, 5 meters plus 1 meter per second equals 6. Because, for one thing, 6 what? 6 meters or 6 meters per second? We're mixing 2 different vectors there. It doesn't make sense, okay? But if he walked 5 meters east and then 1 meter east, we could say, okay, so overall he's 6 meters east. Okay, so vectors of the same quantity can be added, but you can't mix them. It just doesn't make sense, right? They don't add that way. Okay, so we've already done a good amount of this, of adding vectors in 1 dimension, but let's just do some warm-up examples, more of those to remind ourselves of those basics, because having those down is going to help us a lot as we take the next step here into 2 dimensions. We're going to make sure we draw our vector addition diagrams now while it's nice and simple in 1 axis, because having a good grip on that is going to be super helpful when things get more complicated in 2 axes. All right, so John walks 400 meters east, then 600 meters west. What is his resultant displacement? So this is in 1 dimension because it's all happening east-west, right? It's all happening in what we would call our x-axis. East and west, those are our x-axis directions when thinking about a compass. It's not like John is also going north or south, right? He's all just moving in this axis here, x-axis. So I'm going to call this D1, and I'm going to call this D2. Okay, and I'm actually going to go ahead and introduce something now. I'm going to call this D1x, okay, and D2x. Might not seem, super relevant now, but later when we're mixing x's and y's, we're going to want to keep track of, what's in one axis and what's in the other axis, okay, because it's going to be super important to keep them separated as we go to add, okay. Again, just reminding ourselves of the basic skills here. So we want to figure out his resultant displacement. Always, let's start with a vector addition diagram. So we're just going to draw these one at a time, tip to tail. Okay, so first, John walks 400 meters to the east. So I'm going to draw a vector to the east. We'll call that D1x. Okay, then he walks 600 meters to the west. So now, tip to tail, where this one finished, I'm going to start drawing a vector to the west. Okay, now, 600 is bigger than 400, so I need to make sure I draw this westward displacement larger, okay? And it doesn't need to be perfect. You don't need to break out the ruler necessarily, but we know that 600 is, 1.5 times larger than 400, so I'm going to do my best to do about 1.5 times larger, okay? So that is D2x. And now to visualize what we're actually looking for, right, the resultant displacement, we can draw on our vector addition diagram from where we started to where we finished. So he started here, okay, and by the end, he was here. So that is our resultant displacement, dr, displacement resultant. In fact, I'll call it displacement resultant in the x-axis, though in this case, that is just his resultant displacement because all that happened was displacements in the x-axis. Okay, now, since these are both just in the same axis, we can just go ahead and add them up to find our resultant displacement. Okay, but don't forget, we're dealing with vectors. We need to be very careful about signs. Okay, so here we're thinking x. I'm going to go ahead and define east as the positive x direction and west as the negative x direction. So to find the resultant displacement, we're just going to take all of them and add them up, right? The resultant displacement in the x-axis is going to be the result of adding D1 in the x-axis plus D2's x-axis component. So in this case, since D1 was to the east, we're going to take positive 400 meters, and we're going to add D2, which was 600 meters to the west. Well, west is negative, so we're going to add negative 600 meters to find that his resultant displacement is negative 200 meters. Okay, so there's our raw answer. But again, we know that negative really means something here, right? Negative, we know, is what we defined as the west direction. Okay, and since his only displacements happened in the x-axis, his resultant displacement in the x-axis is actually just his resultant displacement. So his dr is going to be 200 meters to the west. So what does that tell us? Well, it says that overall, from where he started after doing all of this stuff, he's 200 meters to the west of where he began. Now, again, I know you might be thinking, come on, I could have just done that in my head, right? But that's not the point here, okay? We're solidifying these concepts and these skills because we're going to need them when things get more complicated, okay? So we want to be confident with it in one dimension before we take it to 2 dimensions, okay? Now, something I want to point out here, right? We can always go back. We don't have to just draw this once and then forget about it. The whole point of drawing it is to help us along the way, right? So sure enough, right, from this, we were expecting, okay, he should end up to the west of where he started based on our vector addition diagram. Well, good, we got that, right? And he should be, not quite obviously as big as this one, not as big as this one. Well, yeah, 200 meters is smaller than 400, smaller than 600. So based on what we were expecting with our vector addition diagram that gave us our bearings, we're getting a reasonable result here. Okay, let's go ahead and try this one out. So Dave drives 5 kilometers north. Okay, I'm going to call that D1, and I'm noticing again that D1 is entirely in the y-axis, right? North is a y-axis direction. Then 3 kilometers south. Okay, so still entirely in the y-axis, right? Opposite direction, but same axis. And then 1 kilometer north. So again, this is actually all in one dimension, right? We're just dealing with north-south. There's no east-west also going on, okay? We want to know Dave's resultant displacement, okay? So, as always, let's start with a vector addition diagram. First up, 5 kilometers north. So I'll draw a vector representing a displacement of 5 kilometers north. Then tip to tail, 3 kilometers south. So at the tip of this one, now 3 is not as big as 5, so I'm going to draw it not as big as 5, okay, D2. And finally, 1 kilometer north, okay, so again, that's even smaller. So D3 is going to be even smaller. Gets a little crowded when they're all on top of each other like this, right, okay? But now to visualize our resultant displacement, we go from where we started to where we finished. So we started here, we finished up here at the top of D3. So from there to there, that is our resultant displacement. So right off the bat, look at all the predictions we can make, right? Just from a quick sketch. We know that he should end up north of where he started, right? And, less than 5 kilometers north of where he started, roughly speaking, okay, because it's not as big as D1. Okay, let's now go ahead and start adding them up to find the resultant displacement. I'm about to add vectors, so I better make sure I define my directions. In this case, everything's happening in the y-axis, okay, so I'm just going to define north as the positive y direction and south as the negative y direction. And then since everything's happening in the y-axis, all of these are entirely in the y-axis, north or south, right? Then our resultant displacement is just the resultant displacement in the y-axis, right? So D1's y plus D2's y plus D3's y. Since they're entirely in the y, that's just the vectors themselves. So let's go ahead and add these up, being careful about our directions. So note that I made sure to make the 3 kilometers south have the opposite sign of these two that were to the north, but adding those all up, I get that his overall resultant displacement is going to be positive 3 kilometers, okay? And what does that mean? Well, for us, that means he is 3 kilometers north of where he started. We define north as the positive direction in the y-axis. We added up all these vectors that were all in the y-axis and we got a positive. So our answer is to the north. 2 significant digits. There we go. There's our final answer. Okay, now we're gonna start going into 2 dimensions here. I know in 1 dimension it seems like a lot of stuff going on to really do something that we probably could have basically done in our heads, right? But the important fundamental skills there are what we're focused on. Now, before we dive fully into 2D vectors, we're going to need a few tools in our kit from previous science and or math courses. So let's do a quick recap of everyone's favorite, trigonometry. So trigonometry is essentially the study and analysis of triangles, right? And the reason it pops up here is that so much of physics in 2 dimensions boils down to ultimately analyzing triangles. You'll be amazed at how much of this is just being able to draw and analyze and pick apart a triangle. Okay. For example, if someone walks, east and then north, we can start to visualize and analyze that with a triangle. Or maybe they walk at some angle between north and east. Well, we can start to break that down and analyze it in terms of a triangle. So first up, one of the most important tools in analyzing triangles is the good old Pythagorean theorem. So what this says is if we have a triangle like this, then c squared, this side, will be equal to a squared plus b squared. So the really important thing to remember with the Pythagorean theorem is that this c, the side that's by itself being squared, must be the hypotenuse. Okay, so the hypotenuse, reminder, is the side that's across from the right angle in a right angle triangle. That's the hypotenuse. Okay, these 2 sides, we call them the legs. They're the non-hypotenuse sides. It actually doesn't matter in the formula whether you switched that around. If you wanted to call this side A and this side B, that would be fine. You would get the same result because you're just adding them anyway. And addition, it doesn't matter what order you do it. But you will get the wrong answer if you call this side, if you put this side into the formula there, that'll give you the wrong result. Okay, so the hypotenuse needs to be the side that you're calling the c squared, right? The one by itself. And you'll note that this is on your formula sheet, okay? There is a trigonometry and geometry section of your formula sheet. You can see the Pythagorean theorem right there, okay? We are also going to remind ourselves of the trig ratios because we know those are a very helpful tool for analyzing triangles as well. So remember these, you know them, you love them, it's SOHCAHTOA, right? And these are just ratios, okay? They're ratios of one side of a triangle to another side of the triangle. Depending on which 2 sides you're talking about, that lets you know which ratio you should be thinking about, right? So we say that the sine of an angle, theta, okay, Greek letter representing angles, is equal to the side opposite to that angle. So that means across from, right? If we were interested in this angle here, well, then the sine of that angle would be equal to the ratio of the side opposite across from it to the hypotenuse, right? And there's our hypotenuse. Hypotenuse, once again, the side across from the right angle in the triangle. So all the sine of this angle would be what you get when you take opposite and divide it by hypotenuse. Sine of theta is equal to opposite over hypotenuse. Cosine of theta would be equal to the side adjacent. Adjacent meaning next to, right? So you might be saying, but hang on, there's 2 sides adjacent to our angle, next to our angle. True, but one of them already has a name. That's the hypotenuse, right? So cosine of an angle is equal to adjacent side, however long that is, divided by the hypotenuse, okay? And finally, the tangent, or tan of an angle, is the ratio of the side opposite to the side adjacent. So for tan, we would take this side and divide it by this side, opposite over adjacent. That's all SOHCAHTOA helps us remember, right? Opposite hypotenuse, adjacent over hypotenuse, and opposite over adjacent for sine, cos, and tan, okay? Now again, important reminder, okay, don't forget, adjacent just depends on what angle you're thinking about. So for the same triangle, if we were instead interested in this angle up here, right? Well, now this side is adjacent to that angle, right? So this would be a different angle, right, than this one. But that's okay because the cosine of this angle is going to be a different ratio. Adjacent is now this side, right? So remember that what's opposite to one angle is going to be adjacent to the other angle. So diagrams are your friend here. They always help out. Often when I find students are like, I don't know what side's opposite or adjacent or hypotenuse, I look at their work so far and they haven't drawn a diagram. So that's my number one thing I'll say to them. I'll say, well, first, draw your diagram. Okay, let's get a quick refresher here. how could we find the hypotenuse below if we knew the side labeled A, so we have that, and the side labeled O, so we also have that side, right? Okay, so if we knew those two things, what could we use to find H, the hypotenuse? Well, we know two sides. We want to know the third side. That means we can actually use Pythagorean theorem, right? So hypotenuse, right, needs to be, we could say that H squared is equal to the other two sides squared and then added. So A squared plus O squared. And again, the really important thing there is that this side needs to be the one isolated, right, by itself, H squared. Okay. Now, what if we wanted to know the side, if we still want to know the hypotenuse, okay, but we now know the side labeled A and we know the angle theta. Okay, so now we don't know two sides. We can see we can't use the Pythagorean theorem. We would have two things we didn't know in this equation, okay? But if we knew this side and the angle, right? Well, that means we can probably use a trigonometric ratio, right? And we can look here. We want to know hypotenuse. We have the side that is adjacent to our angle, right? So we have the angle and we have the side adjacent to it. We want to find the hypotenuse. Well, if I look at right, sine, that's not going to work because I don't know the opposite side, right? What about cosine? I know the angle, so cosine of the angle, right, is equal to adjacent. Okay, I have the adjacent side, and I want to know the hypotenuse. Well, that's perfect, because I know everything I need in this formula except for the one thing I'm trying to find, which means I can use this formula to find that hypotenuse. So to do this, I would need to write out the ratio that the cosine of theta is equal to adjacent over hypotenuse, right? And again, you have these on your formula sheet here. You have all of them. So if you can figure out what sides of the triangle you have or want to know, and as well as the angle, right, you can write out the equation. And then this is a solvable equation because I know this and I know this. So with some rearranging, we could solve for the hypotenuse, right? So all I did there was multiply both sides by h, divide both sides by cos theta, right? Cos of theta, if we know that angle, that's something we can just put in our calculator using the cosine button, right? If it was 20 degrees, cosine of 20. Divide our adjacent side by that, and we would have the hypotenuse. Okay, now what if we had the side labeled O and the angle theta? So now we know this side and we know this angle. So I have an angle, and the side that is opposite to it, I want the hypotenuse. So opposite, hypotenuse, opposite, hypotenuse. Sine theta will work for that. And there we go, right? I have opposite, I have the angle, I can solve for hypotenuse now. It would look very similar to this, except a sine instead of a cos. All right, let's get some practice. Let's take a trip down memory lane and do some good old grade 10 trigonometry. So we want to calculate the indicated angle, knowing this side and this side. So it's still the same problem-solving thought process, right? We have an unknown and we have things we are given, okay? So if we want to find this angle, well, what do we have relative to that angle? We have this side, which is across from our angle. That is opposite, right? And then we have the side across from that should really be drawn in as a right angle, whoops. We have the side across from the right angle, that is the hypotenuse. So ask yourself, okay, we have opposite, and we have hypotenuse. Opposite, hypotenuse, and we want the angle. What does that make you think of? What ratio or equation? Right, sine theta. So sine is equal to opposite over hypotenuse. So let's write that out. The sine of an angle will be equal to the side across from that angle, so 12 meters, divided by the hypotenuse, so 18 meters. Okay, so this is an equation we can now solve, right? We only have one unknown variable. Whenever you have an equation with only one variable you don't know, you can solve for that variable. In this case, theta. So be very careful. We right now do not have, 12 over 18 does not equal theta. It equals the sine of theta. So we need to undo the fact that we're taking the sine of this angle. Sine is an operation. So if you had any of these scenarios, what would you need to do to solve for x, right? Well, here, okay, x plus 2 equals 5. We're adding 2 to x. That's why we don't know it. So in order to undo that, we need to do the inverse operation of adding 2, which is subtracting 2, right? So we would subtract 2 from both sides to find that x is 3. Or here, x is being multiplied by 2. To undo that, we need the inverse operation of multiplication. We would divide both sides by 2 to find that x is 4. Or even here, x is being squared. So how do we undo that? The inverse of squaring is square rooting to find that x is 3, okay? And so it's the exact same idea here. We don't want sine theta the same way we didn't want to know x plus 2. We just wanted to know x, right? We don't want to know sine theta. We want to just know theta. So we need to do the inverse operation of sine to both sides, right? And the inverse operation of sine does not have a very creative name. It's actually just called inverse sine. And it just looks like this. Now, we honestly normally don't show this actually doing it to both sides just because it kind of gets messy, okay? But that's what the inverse, taking the inverse sine of both sides looks like. So on your calculator, if you look at the sine button, above it, there should be a little sine minus 1 sign, okay? You get that by pressing second function or shift on your calculator. So you're going to do second sine when we get to the step where we're actually putting our calculations in, okay? But all this does, the inverse sine undoes the fact that we're taking the sine. And what I do to one side, I must do to the other. So we get that theta will equal the inverse sine of 12 over 18. So just since it may have been a while, I'll show you how to actually put this in your calculator, okay? Now, I won't do it for every single one, and your calculator might look a little bit different, okay? But generally speaking, you can see here, if you look at the sine button, right? Up above, there's the sine to the minus 1. That's inverse sine. So we want to do second sine of 12 divided by 18 to get what this angle is equal to. And when I press enter, I get that that angle is 41.810, etc. degrees. And so for SIGDIG rules here, it's not quite as cut and dry as just the least number of digits. So I usually say the same number of decimal places, okay? So we had no decimal places, so I'm just going to round this to 42 degrees. There we go. We solve for the angle using a trig ratio. Now we want to calculate the length of the unknown side, but it's the same process, right? As always, what do we know? What do we want to know, right? Well, here we know the angle. We have the hypotenuse, very good. And what do we want to know? We want to know the side adjacent to our angle. So adjacent hypotenuse, adjacent hypotenuse. What trig ratio works for that? Right, cosine adjacent hypotenuse. So the cosine of 30 degrees will be equal to adjacent x, which is what we want to find, divided by hypotenuse, which is 15 meters. Okay, and we've set up our equation. There's only one thing we don't know. It's x, okay? But right now it's not isolated, okay? In order to isolate it, well, what's happening to it? It's being divided by 15 meters. What's the inverse operation of division by 15 meters? Multiplication by 15 meters. So we see that this unknown side x is equal to 15 meters times the cosine of 30 degrees. Let's just put that in our calculator. So I'll do 15 times, now I don't want inverse cos, I just want regular cosine of 30 degrees. Okay, press enter to find that that would be our unknown side's length. Quick note here, you're going to want to make sure you're in degree mode. Every calculator is a little bit different. I use this one because this is the most common type of calculator students have, okay? But you might need to Google your calculator model to see how to do it. For these ones, right, make sure your mode is in degrees. That just tells our calculator that if we tell it an angle or if it tells us an angle, we want it to be measured in degrees, not radians. Radians you'll encounter in Math 30. For us in Physics 20, it'll always be degrees. All right, there we go. So there's our little reminder of, the grade 10 trigonometry you're going to need here now in Physics 20 and beyond, okay? So now let's go back and kind of think more physicsy about this. Remember, a lot of this is going to have to do with direction. And so directions in 2 dimensions are not going to be as simple as just saying, north, east, up, down, left, right, those kinds of things, right? Because we're going to be dealing with stuff that's sometimes, a combination of up and right, or a combination of west and south, okay? And in order to do those things, we're going to need angles. So a 2-dimensional direction will always include an angle, and sometimes, if the question did it, a reference to a compass direction, what we sometimes call cardinal directions. So it's always okay. There are 2 main systems you can use to communicate. It's always going to be okay to use Cartesian directions, we call them. Those are just angles from 0 to 360. We'll see what they look like in a second here, okay? But as a reminder, the general rule for a Cartesian angle is that we always measure it starting from the positive x-axis. We call that 0 degrees, and then we rotate counterclockwise, so the opposite way a clock goes. So we would measure it, we always start from here, and we would say 0, 90, 180, 270, and finally 360, back to where we started, okay? So if I, for example, wanted to communicate the direction of a vector that was pointed like this, right? So kind of uppy and righty, right? How would I communicate that in Cartesian coordinates? Well, I would say it's, let's just say it's 40 degrees. That tells the person that, okay, if it was starting from here, you'd rotate 40 degrees counterclockwise, and then you'd be aiming the vector in the right direction. But what about if we had a vector like this, right? Okay, well, same thing. We would say starting from here, right? We're going to rotate counterclockwise past 90, past 180. Maybe that's about 220 degrees. And what that communicates to the person reading is that the vector is pointed in this direction, kind of downy, lefty, right? 40 degrees past 180. Okay. The other system we can sometimes use, as long as the question refers to compass directions, those north, east, south, and west cardinal directions we call them, okay, then we can sometimes reference those in our answer as well. Okay, so it's kind of tough to wrap your head around until we see an example, but if the question refers to the compass directions, we can refer to them in our answer. Common student mistake is to include north, east, south, west when the question didn't actually tell us that the directions were north, east, south, or west. Okay, there's always going to be 2 correct ways to do those, as long as you are careful to use the correct angle and reference them properly. Okay, so I know, again, it's a little easier to see once we do some examples, so let's do some examples. We're going to determine all 3 possible ways to express the direction of each vector shown below. So what we're doing here, right, we're saying there's 3 different directions we're going to think about. It's just 3 examples rolled up in one, right? But what we're saying is, what if you had something that was aimed in this direction, right? How could you communicate that to somebody so that they know exactly what you mean, right? Sometimes students will say, well, you could just say it's northeast, right? But that's not really good enough because all of these directions are northeast, right? They're between north and east, right? We need to be a lot more precise because if I'm giving a friend directions and I tell them, go northeast and they walk like that, well, by the time they get there, they're going to be in a very different place than where I wanted them to be, right? So we need to be more specific. It requires an angle. So there are 3 ways we could communicate this angle because it did reference north and east. So the first would just be our Cartesian directions. That's just from 0 to 360 going counterclockwise. Okay, so in this case, it's actually nice and simple. We could just say, well, if I wanted to tell someone how to walk in that direction, I could say walk at 30 degrees. So starting facing east or 0 degrees, rotate counterclockwise 30 degrees, and then start walking, right? That is one way to communicate that direction. But another perfectly valid way of doing it is to actually reference the compass directions. And there's 2 ways to do it. So I could say, starting from east, turn 30 degrees towards the north, right? So that would leave you 30 degrees north of east. Okay, the order there is very important. 30 degrees north of east. Okay, the other 3rd and final way to do it is to tell them starting from north, rotate towards the east, right? So then we would say, starting from north, you would need to rotate, well, how far to get so you're facing in the right direction? You would need to be 60 degrees, right? From 90 to 30 there, that's 60 degrees east of north, right? From north, we want to end up 60 degrees east of it. So notice there, the order, super important. If I say 60 degrees north of east, that's going to be the wrong direction. This would be 60 degrees north of east, right? So always from where you start, right? That's where you're ending east of, or in this case, we started east, so we end up north of it, right? Think about, if you walk south of your house, right? You end up south of house, not house of south. Same idea here. This is 30 degrees north of east or 60 degrees east of north. But these orders matter, okay? You can't flip those around or you're saying the wrong thing. Okay, so all three of those are valid ways to communicate something pointed in this direction here. Let's now think about how we could communicate a different direction. What about something pointed kind of, up and left or somewhere between north and west? I'm just going to erase these to not get too crowded, okay? So first up, we can always use Cartesian directions. So that means, again, starting from 0, right, the positive x-axis, we just rotate counterclockwise. So 0 past 90 all the way to, it looks like, 115 degrees. So we could just say 115 degrees, and because we have these systems in place, people will know what we mean, right? As long as they understand Cartesian directions. So that works. That's a valid way to communicate a vector that's pointed in this direction. But there are two other ways since they referenced compasses here. So we could say, starting from north, you want to go this many degrees towards west, right? So that's going to be, if north is like 90, we're at 115, we could say go 25 degrees west of north or north of west. Right, west of north, right? You want to go 25 degrees to the west of north, right? Or the flip side of that, we could also say, well, starting from west, you want to go, right, 90 minus 25, because this is 90, so if you take away that 25, we get 65 degrees north of west, right? Starting from west, go 65 degrees north of it. All three of these correctly communicate this direction here. So you could see it written any one of those ways. You do need to be able to understand what it means and work with it and come up with your own directions as well. Okay, let's do the last one here. I'm going to encourage you, pause the video and see if you can come up with the 3 ways to communicate something pointed in this direction before I go ahead and do it. Okay, so pause, try it out. All right, in Cartesian directions, right, 0 to 360, 0 past 90, past 180, all the way to, it looks like 220 degrees. Or, okay, we could say starting from west, you need to go 40 degrees towards the south, right? So we could say 40 degrees south of west. Totally works, right? We're going to start from west and go 40 degrees south of it. What's the third and final one? If you didn't pause and do them all, at least pause and try this one on your own, okay? We could also say, starting from south, you need to go towards the west. How far? 50 degrees. So 50 degrees west of south, right? Again, the order there is important. Saying 50 degrees south of west would be wrong. That would be a different angle, right? But saying 50 degrees west of south works the same way saying 40 degrees south of west also works, as long as you get those orders correct. So that's what it's referring to here, where it says there's 2 correct ways to give cardinal directions, but you need to be careful to use the correct angle and the correct order of your directions. You do need to think about south of west versus west of south. Those are two different things. Okay, let's go ahead and start putting these ideas together now. We've kind of built up all the basic skills and we're ready to put them to use. So here we want to find the magnitude and direction of the resultant velocity vector. So that's the result of adding those two for the two component vectors below. So here we go. We are now entering 2D motion, right? Something to the right side of the page and something towards the bottom of the page. Two different axes. We know we cannot just add 12 and 9. That wouldn't make sense, right? We need to think about this a bit differently because the 12 and the 9 are not in the same axis. So they've actually already drawn part of our VAD for us. That was nice of them, right? They said tip to tail, 12 meters per second to the right, 9 meters per second down. But what we want to know is overall, what's that velocity? If in the x-axis you're moving at 12 meters per second, while at the same time in the y-axis you're moving 9 meters per second. So we'll call that our resultant velocity, right? And how did I get that? Well, they added them tip to tail. The resultant is just from where our diagram started to where it finished. So do you see our triangle here, right? This is why VADs are so important. Often they give us the triangle and then we just need to solve the triangle like we're back in Math 10, right? So if I had these two sides of a triangle and I wanted to know this side, what could I use? Right, I could use the Pythagorean theorem, right? So I have to make the hypotenuse the side by itself, but this means our resultant velocity squared is going to equal the sum of these two sides squared, right? C squared equals A squared plus B squared, Pythagorean theorem. Okay, now we don't want the velocity squared, we just want the velocity, so we can go ahead and square root both sides. But then we're ready to go ahead and square them, add them, and then square root them. Okay, be careful. Sometimes students will do this. They'll say, oh, square rooting and squared, those cancel out. But they don't because of the fact that we also have an addition going on. Okay, we need to square, then add. We can't just undo that square rooting like that. So we square both of these, right? 12 squared is 144, 9 squared is 81. Add them now to get 225. And finally, square root to actually just get 15 meters per second. So that is, now be careful, that's the magnitude of our resultant velocity. So that's how fast it is, but we still need to give the direction, okay? So we've got how fast it's going in this direction. We just haven't said what that direction actually is yet, right? And we cannot just say, oh, it's kind of downy righty. That's not good enough. Because there's a million directions that are downy righty, right? We need to be more specific and actually give the exact angle. And so once again, this is why I keep emphasizing the importance of those vector addition diagrams, because now this shows us what the angle is that we're kind of looking for, right? We can use our VAD to say, okay, if I found that angle, I'd be on my way to describing which direction we need to say, right? Now, important side note here, sometimes students will find this angle, okay? But that doesn't really make sense, right? I mean, you could find it and then use it to find this one, but this will not be our answer for our angle. And the reason for that is our velocity is directed this way, right? We're essentially saying which way is it aimed. Well, you don't aim from the end of the vector. You need to aim from the beginning, right? Think of, throwing a ball and aiming. You can't aim from where it lands. You have to aim from where you threw it, right? So this angle is going to communicate our direction, right? Notice up here, we were always finding the angles from the beginning of the vector. We weren't saying, okay, well, what's, over here, what would be this angle, right? That wouldn't make sense. Okay. So how can we figure out that angle? Well, we've actually got options because we have the hypotenuse, we found it. We also have adjacent and we have opposite, right? So we have all three sides. We could do whatever we wanted here, really. However, I do suggest, when possible, use as many values that the question gave you as you can, because these are right? If we made a mistake here and then we use this, well, now our angle's going to be wrong too, right? At least we know for sure that this has to be 9 and this has to be 12 because the question straight up gave them to us. So using those two, we've got opposite and adjacent. What does that make you think of? Opposite, adjacent. Tan, right. Tan of an angle is equal to opposite over adjacent. So for us, that means tan of our unknown angle theta needs to equal opposite, so 9 meters per second, over adjacent, so 12 meters. Okay, almost there, but we don't want tan of theta, we want theta itself, so we need to take the inverse tan of both sides. Find that theta is 37 degrees. Okay, now, be careful. If I just say that this velocity is 15 meters per second at an angle of 37 degrees, people are going to think I mean this, right? Just saying 37 degrees means starting here, go counterclockwise 37 degrees, indicating that our velocity is in this direction. Well, that's not what we wanted, right? So this is, for those of you that have taken Math 20, we would call it like our reference angle, right? It is the angle between these two lines, but to place it properly in the full picture here, we need to think about where it actually is, right? So we know we're kind of down and to the right, right? This is our velocity resultant, okay? And we know that this angle here, so between the horizontal and our vector, that angle we now know is 37 degrees. So see what I mean, right? Pictures are your friend. Our VAD has come back to help us a few times now, because now we can visualize where that 37 actually goes, okay? So in order to properly communicate it, well, we know this would be 0, 90, and then all the way around until we get back to where we started at 360, right? So to communicate this angle, we need to say, okay, starting from 0, go counterclockwise until you get that far, right? And so how could we communicate that? Well, 360 would be all the way around. We stopped 37 degrees before that, right? If we had gone another 37 degrees, we'd get all the way to 360. So to communicate this direction, we can say 360 minus 37 degrees that we left out to figure out that our actual angle for the direction of this would be 360 minus 37 is 323 degrees. And there we go. That's how we can communicate our angle in Cartesian coordinates. So putting it all together now, we need the magnitude. So it's moving at 15 meters per second, and it's doing that in the direction of 323 degrees. Okay, people will know what we mean by that as long as they understand their Cartesian directions. So notice we didn't use the cardinal, the compass directions here, because no one actually told us that this was east and this was south, right? All we know is that it's drawn like this. I mean, this could just as well be to the right and down, right? So we don't know, so it's safest just to say Cartesian coordinates 0 to 360, those always work. Okay, let's try another one here. So Jack goes for a walk in the woods. He walks 4 kilometers north, and then he turns and walks 8 kilometers west, so 2 different axes. What is his final displacement relative to his starting position? So displacement, vector, needs magnitude and direction. Okay, they didn't draw their vector addition start the vector addition diagram for us this time. We're going to have to draw our own. So first, he walks 4 kilometers north. I'm going to go ahead and draw that here. 4 kilometers north. Then he walks 8 kilometers west. So tip to tail, I'm going to draw 8 kilometers west. 8 is about twice as large. Well, not about. 8 is twice as large as 4. So I'm going to draw this about twice as large as 4 so that it gives me the right idea. And so to figure out his resultant displacement, right, what we would call dr, resultant displacement, we just say, okay, if he did those two things, then he started from here and he ended up here. So his resultant displacement is that, right? How big is that and in which direction? Well, that's what we need to find out. So again, right, look how much our VAD helps us here. Now we can see, aha, we just have a triangle, right? He went 4 kilometers north, 8 kilometers west. So what is this distance? 2 sides of a right angle triangle. We want to know the third. What can we use? We can use Pythagorean theorem. Very good. So let's write it down. And then we'll go ahead, square these, add them, and then square root to get our resultant displacement. Okay, so doing that, now remember, we're not going to round to significant digits until we're stating our final answer, okay? because we might need to use that number again and again and again, right? So we don't want to over round. Okay, so using the Pythagorean theorem, I've now found the magnitude of his displacement, so how far this is from here to here. But what I haven't described is in which direction, right? To do that, we're going to need an angle. So once again, we can look at our vector addition diagram here, and we can see, we can use it to say, okay, well, this angle would work. If I could find that angle, I could use it to communicate direction, right? And now our VAD helps us out because we can say, all right, well, I know that opposite is 8 kilometers, adjacent is 4 kilometers, right? Opposite, adjacent, opposite, adjacent. Hey, once again, tan will help us out here. So step 2, let's find that angle. So tan of theta equals opposite, 8 kilometers, over adjacent, 4 kilometers. And therefore, theta equals the inverse tan of 8 over 4. Putting that into my calculator, again, that would be second tan or shift tan, depending on your calculator. I got that angle was 63 degrees. Now, once again, we have to be careful. If I just say 63 degrees, right, they're going to think I mean something like this, right, in that direction. Well, our VAD, we know that that's nothing like the direction we want. So we have to be able to think about this and how it relates to the, all directions in 360. So they did mention north and west here. So we could actually get away with saying, okay, in this case, if we look at how we've drawn it, our most likely answer here, we would probably say, starting from north, go 63 degrees towards the west, right? 63 degrees west of north will leave us pointing in this direction, okay? Careful, not north of west. So there's one of our possible answers. To 2 significant digits, right? 8.9 kilometers, 63 degrees west of north. Or for our direction, we could have also said, right? I mean, we probably wouldn't because of how we drew our VAD, but we could have just as easily said, well, here's west, here's north, right? We could have just as easily said, instead of west of north, we could have said 27 degrees north of west, right? That means the same thing, right? So 27 degrees north of west would also be a valid answer, okay? And finally, we could even do it in the full Cartesian coordinates from 0 to 360 and say, all right, well, now I know that is 63 degrees. So if this is 0, this is 90, right? We went past 90 by 63 degrees, so that's 90 plus 63, or 153 degrees in Cartesian coordinates, right? So even that would be an acceptable way to communicate the answer. Which one you choose really probably most of the time is going to boil down to just how you set up your VAD, right? If you chose to draw 8, then 4, you probably would have, from your diagram, found the north of west version of our answer, right? If you drew it like we did, with first the 4, then the 8 to the west, this one makes the most sense just because that's how your triangle looks, right? You're looking at the west of north angle, right? Again, the Cartesian one, totally valid as well. All 3 can be used. All 3 are correct, okay, as long as we, write them correctly and we don't mix up things like west of north with north of west. Okay, so before we move on here, just a little reminder of what we just did, right? In both of those examples, what we found was what we call the resultant vector. It's the result of adding the other 2 together. And again, we can think of that as the single vector that gives us the same result as adding up all of those components together, right? For example, you could walk 4 kilometers north and then you could walk 8 kilometers west, right? You'll be in the same place as if you had just walked 8.9 kilometers at 63 degrees west of north, right? That's what this is. It's the result of doing all of these component vectors. Same idea here. If something's moving 12 meters per second and 9 meters per second in these directions, then overall, it's just like moving 15 meters per second at an angle of 323 degrees. Okay, now, time to start talking about the x and y components of vectors that are in multiple axes at the same time. because we haven't actually seen that yet. So far, in all of these examples, the vectors we've been working with have just had components in one axis or the other. What I mean by that is, yes, we have some x stuff and some y stuff going on here, but each individual vector was entirely x or entirely y, right? 4 kilometers north, and then 8 kilometers west. They weren't walking in just one part of their journey. They weren't walking off at an angle, right? We had to add them up to find the resultant that would be at an angle, but individually those vectors were just all x or all y. But of course we know that you don't have to just walk north or just walk east, right? You can walk off at an angle. So often in many of the more realistic scenarios we're going to look at, we're going to need to add vectors that don't act perfectly along one axis or the other, but instead have components along both axes. And so in order to do this, we're going to need to first find those components in the x and y axes. So for example, right, if a ball has a velocity like this, where it's directed at some angle between up and right, so it's moving in this direction, right? Well, it is moving up, and it is moving right. It's just doing both at the same time, right? Overall, its velocity looks like this, but we can still think about how fast it's moving vertically and how fast it's moving horizontally while it's moving at this angle, okay? And that's the idea of a vector component. So its velocity does have an x component. You can think of that since it's moving up and right. The x component is like the rightness of the ball's velocity, and the y component is like the upness of the ball's velocity, right? And therefore, with trigonometry, you can see that if we knew the angle at which the velocity was directed, we could find those x and y components with trigonometry. So for example, if we were told that this ball's velocity was aimed 40 degrees above the horizontal here, right? We could then use that if we knew the velocity to figure out, all right, well then how fast is it moving just horizontally and how fast is it moving just vertically? The x and y components of its velocity. And that's going to be crucial for where we're headed when we actually start analyzing vectors that are not just straight north and not just straight west, but actually doing both of those things or any combination of other directions. Okay, so we're going to get some practice here first with separating vectors into their x and y components. And before we really dive in, I just want to emphasize, okay, sometimes I find students overthink this a lot, right? All we're doing is if we have a vector, say like that, that's kind of, uppy righty, right? Its x component is just righty. Its y component is just uppy. We're just saying how much is it going up, how much is it going to the right, right? If we have one like this, downy righty, what do you think its x component is? It's how much it's to the right. And what do you think its y component is? It's how much it's down, right? Something like this, so kind of down and to the left. Well, we just said it. Its x component is to the left, that far. Its y component is down, that far, right? All we're doing is taking a vector and separating it. Since it's a combination of two directions on our axes, we're separating it into those two components, right? If it's downy lefty, well, how much is it lefty? How much is it downy, right? If it's righty downy, how much right? How much down, etc. So this one wants us to separate a displacement of 10 meters at 330 degrees into its x and y components. So first things first, we got to draw this out and just figure out what does 10 meters at 330 degrees, mostly that 330 degrees, what does that actually look like? Okay, so what direction is 330 degrees, right? Well, okay, starting from 0, right? We know that we're going counterclockwise past 90, 180, and 270, but not all the way around to do a full 360. So there we go. We now have a rough idea of which directions our vector is pointing, right? It's somewhere kind of righty and downy. So our vector looks something like this. That's which direction the displacement is. Now I've drawn it twice because I'm going to show you that there's two different ways we can approach this. Both are perfectly valid, okay? So let's separate. If something's down and to the right, what's its x component like? Well, it's to the right, right? And what's its y component like? Well, it's down, right? That is the rightness of this vector. That is the downness of this vector. And then sometimes students will say to me at this stage, they'll say, but what if I drew it like this? Am I going to get the wrong answer? Right? What if I had gone first, the y component looks like that, and then the x component looks like that, right? Will I get the wrong answer? No, those are both perfectly valid, right? So in both cases, we would say this is our displacement, this is its x component, and this is its y component. So you do not need to draw both, okay? I'm just showing you that you get the same result either way. So it's kind of whatever comes to you, as long as you're careful about the angles involved and the geometry involved, these students would both get the right answer, okay? All we're saying, once again, is that if your displacement looks like this, right? Well, then horizontally, that's how far you're going, and vertically, that's how far you're going. If you walk at this angle, essentially, right, how far are you going to the right, and how far are you going down? Okay, so with that in mind, now you can see how triangles are coming into play here. In order to do trigonometry to actually figure out those values, we need to get an angle in that triangle. Well, that's where this can come in again and help us, right? So looking at this here, we could say, okay, so to the horizontal, what is this angle? Well, in that case, right, we know that this was 330, so what was left to a full 360 would have been 30 degrees. So this angle here is 30 degrees, right? Referenced to the horizontal, 30 degrees. Now, if we had drawn it this way, we would now be looking at figuring out this angle. So be careful, this is now referenced to the y-axis here. So we'd actually need to figure out what's this angle here, right? So we could look at it and say, well, we are at 330, so we're 60 degrees past 270. That's one way to look at it, okay? So different paths, we will both still get the right answer, okay? We're just kind of taking a different route there, okay? So we know that this is 10 meters. In both of these cases, we've got this side and we have an angle. What we want to do is find this side and this side, right? Find the x component and the y component. So we can use trigonometry here. I have hypotenuse. To find x, I want, for this triangle, adjacent. So adjacent hypotenuse, that makes me think of cosine. So the cosine of 30 degrees is equal to adjacent, my unknown, dx, the x component, over hypotenuse, well, that's 10 meters. So to solve for dx, it's being divided by 10 meters. I need to multiply both sides by 10 meters. And so to get dx, I need to multiply cos 30 by 10 meters. And that gave me 8.6602 meters. Okay, so to two significant digits, that would just be 8.7 meters. Now, even this component, it is a vector, right? And so we need to give a direction here. Using Cartesian coordinates, this x coordinate would be, this x component would be at 0 degrees, right? It's pointed at 0 degrees. Our components should just be in the x-axis or y-axis. So either 0, 180 or 90, 270, right? That is, if someone went 10 meters at 330 degrees, what this is telling us is that means that overall, horizontally, they ended up 8.7 meters to the right of where they started, right? Yes, they also moved down, but in terms of just how far they moved right, that's how far, okay? Now, flipping the question to say, okay, so then how far did they go down if they went 330 degrees, 10 meters at 330 degrees? That's now finding the y component. So the y component, based on our triangle here, is opposite, right? And we have hypotenuse still. So opposite hypotenuse, that makes me think of sine, right? So, katoa. So let's set up the ratio to find our y component of this displacement, right? And so, sure enough, right, sine of 30 equals opposite over hypotenuse. Multiply both sides by 10 meters, and we get that vertically they moved 5 meters, okay? Now, as for the direction of this one, well, look, right? This is, again, our diagrams are so helpful. Which way is that? Well, we would call that 270 degrees, right? Straight down towards the bottom of the page, okay? And so all these are, folks, right, is splitting this up and saying, great, okay, you went 10 meters at this angle. You really walked like this. But how far does that mean you move to the right or towards 0 degrees? Well, 8.7 meters overall that way and 5 meters that way, right? You can think of it this way. If you walked 8.7 meters that way and 5 meters that way, you would end up in the same place as someone who just walked at this angle, off like that. Now, you will get the same results if you set it up this way. Okay, the difference will just be that instead of doing cosine of 30 to get your x component, look, you're going to use the sine of 60 because yes, it's a different angle, but now dx is opposite. And sine of 60, guess what, is the same thing as the cosine of 30. You can test it out on your calculator right now, right? Same goes over here. You'll now use the cosine of 60 when finding your y component instead of the sine of 30. Well, cosine of 60 and sine of 30 are the same, okay? So if you don't believe me, you can double check. You should still get the same result as long as you're careful about your angles and your opposites and adjacents and hypotenuses. All right, let's get a little more practice with this. So I'm going to go a bit quicker here. We want to draw these and separate them into their component vectors. 15 meters per second at 35 degrees south of west. So how fast are you moving south and how fast are you moving west, right? That's the y component and the x component. Well, first things first, let's figure out roughly what we're dealing with. So we are 35 degrees south of west. So we know we're somewhere in this quadrant, right? Somewhere between south and west. Now the question is this 35 degrees or is this 35 degrees? What do you think? Right, it is this one because we are south of west, right? 35 degrees south of west means from west we went 35 degrees south of it, okay? So this is 35 degrees, okay? Roughly what that means we're dealing with here, right? We got something that looks like this. This is 15 meters per second. What's the x component look like? Yeah, it looks like that. It's how fast we're moving to the west. What's the y component look like? It's like that. It's how far we're moving to the south. Okay, so we would call this is a velocity. So this is the x component of that velocity, and this is the y component of that velocity. And now we know that this angle here relative to west is 35 degrees. Again, if you drew it the other way, that's okay. You'll just use a sine when I use a cos and a cos when I use a sine. Okay, so we have the hypotenuse. Our velocity itself is 15 meters per second. To get its x component, well, that's the adjacent side. We have hypotenuse. Adjacent hypotenuse, what does that work with? Cosine. So let's set up our ratio. And what we want, the x component is being divided by 15 meters per second. So multiply both sides by 15 meters per second. And to two significant digits, I got that the x component of our velocity was 12 meters per second. Okay, now, which direction is that x component? Well, it's to the west, right? Again, we're saying if you're moving 15 meters per second at some angle south of west, then horizontally you're moving west. Vertically, you're moving south at the same time, but you do have some velocity to the west, and now we know it's 12 meters per second. Okay, I encourage you to pause, try finding the y component on your own, right? But what we're going to do, now we want opposite. We still have hypotenuse. So we're going to use sine of 35. Same idea, right? Opposite is now our y component that we want over hypotenuse, still 15 meters per second. Multiply both sides by 15. And I get that vertically they are moving at 8.6 meters per second towards the south. You got it. Okay, now important to note again, these are not three different velocities necessarily, right? This is all just saying if you're going this fast, then how far are you moving just horizontally and how far are you moving just vertically? Okay, that's all we're saying there. All right, let's try this one out. This is a unit you've seen before, but it might have been a while. It is a Newton. It is a measure of force, okay, which is a vector, right? Now, the point here is to emphasize that all vectors, we deal with them in the same way when doing this stuff, okay? Yes, we haven't talked much about forces, but forces are vectors. We apply the same process. You'll do the same thing in Physics 30 with magnetic fields. They're all vectors. They all do the same thing, okay? The analysis is the same here, regardless of what quantity we're talking about. So, 12 newtons at 120 degrees. First things first, Let's figure out exactly what 120 degrees means, okay? So starting from 0, we know we're going past 90, but we don't make it to 180. So now we know that our force is something like that, right? Kind of uppy lefty. So the x component is, well, lefty, and the y component is uppy. Or alternatively, we could have drawn it this way. Maybe I'll go this way just to mix it up a bit, okay? So now we can see what's happening, right? Our force is 12 newtons. We want to know if that's your force, it's at some angle, right? Well, then how hard is your force in the x-axis? How hard are you pushing, to the left? And how hard are you pushing up? Okay, so in order to do the trigonometry to find those sides, we need to know, let's say, this angle here. So let's look at our diagram and think about what is that angle, okay? Well, if this is 120, right, and we're referencing here to the vertical, to the y-axis, so I need to figure out what is this angle here to match that triangle, right? If you had drawn yours this way and you were looking for this angle, right, you would need to be thinking about this angle in here referenced to the x-axis. And you'd get the right answer. You would just, approach it differently than I'm going to here. So when I look at this, I say, okay, here's 90. We went to 120, so we went 30 degrees past 90. So this is 30 degrees. Right? If you had looked at it this way, you would say, okay, this is 60 degrees because there's another 60 to go from 120 to get to 180. Okay, you'll get the same result. You'll just use sines when I use coses and coses when I use sines. So now to find the x component of our force, we now want opposite and we have hypotenuse, right? X is opposite to 30 degrees and we have hypotenuse. So we need to use sine here to get our x component. Sine of 30 degrees equals opposite over hypotenuse. Multiply both sides by 12. And I get that the x component of our force is 6 newtons. Which way now is this? Well, best we can say is 180 degrees, right? It is towards that left side of the page. Okay, let's do the same for y, except now y is adjacent. We have hypotenuse. We're going to use cosine. So all the same algebra involved. I'm getting 10.39230, so to two significant digits, that would be 10 newtons. And which direction? Right, it's at 90 degrees, pointed straight towards the top of the page there. And there we go. So again, all we've done here, we had some force, we are pushing at some angle, but what we're saying is that if you're pushing 12 newtons at that angle, it's the same as pushing straight to the left with 6 newtons of force, while also pushing straight up with 10.392 newtons of force. All right. So go ahead now, pause the video and try this one out, okay? It's asking you to separate this into its components. Remember, okay, the key steps. First, get your bearings, figure out what it looks like, draw your diagrams, find your angles, and trigonometry will lead the way after that. And if you want a little bit of practice mastering finding these components, because that's a very important skill before we put it all together in the last section here, you could also go ahead and give those ones a try, okay? Or as always, you can kind of finish the lesson and then when you're doing all of the practice, knock those ones out. Okay, here we go. We've now kind of gotten all of the skills we're going to need to put this all together and really be able to add any two vectors in multiple dimensions. Here we go. So, important thing right off the bat, okay? We can only add vectors algebraically, right? Like actually adding the two numbers on our calculator if they are directed along the same axis. In other words, they're both in the x-axis or they're both in the y-axis, right? That's why we need to separate these vectors into their x and y components. Because again, if you have something, that's to the east and to the north, 5 meters east, 4 meters to the north, for example, right? It doesn't make sense to say it went 9 meters because they're not in the same axis. We know through the Pythagorean theorem, it'll actually be, the square root of 5 squared plus 4 squared, okay? So that's why we need to separate into their x components and y components, because if we have two things in the x-axis, for example, then it really does make sense to say that total it went 5 plus 4 or 9 meters, right? So what we're eventually building towards is having, a situation like this where we have multiple things. Now we know we can't add this to this just by adding the two numbers, right? But if we can break them down into their x and y components, then we know that it does make sense to add this thing's x component to this thing's x component to get the total x displacement. And to add this thing's y component to this thing's y component to this thing's y component to get the total y displacement. That's why it's an important skill to be able to separate a vector into its axes components, okay? So we are never going to add an x component to a y component algebraically. We're never going to add vectors with components in multiple axes algebraically, right? It would make no sense to just add if this was 5 and this was 4. It would make no sense to just say, oh, this gives us 9, right? They're in totally different axes, different components and all that. So all we can do algebraically when it comes to actually adding one number to one number is x's to x's and y's to y's. And so this is why we separate into their components. Add the x components separately, add the y components separately, and then we'll talk about where we go from there. But it is always the same process to do this, okay? First things first, draw your diagram, tip to tail, right? And, resultant from tail of the first to tip of the last, okay? Do your best, try to draw it large and reasonably accurate. If you do a good job in drawing it, it'll help you, right? It'll help you understand what your answer should look like we've been doing so far, right? And it'll help you as you go to find other components. You keep coming back to the VAD to help you in your next steps as you go, as you've seen, right? We kept coming back to our diagrams to figure out, okay, what's next? What do we know? Next step is what we were just doing, right? Everything we've done in this lesson was pieces in the puzzle that we're now putting together, okay? So separate all of the vectors, every single one, into their x and y components. Super helpful, as we just saw, to draw a component triangle for each vector, right? So for example, if you know that one part of the journey was 10 meters at some angle, draw it out, right? And then it helps you with your trigonometry and your SOHCAHTOA. Once you've got all your x and y components, if you add all of the x components together, what you get is the x component of the overall resultant vector. So if we want to know how far did we move, just left or right, well, we need to figure out what's the rightness of this plus the leftness of this, right? And overall, that'll tell us how far we moved in the x-axis, okay? Then we do the same for the y-axis. Now that we've got all our y components, right? If I add up all of these y components, then overall, I know roughly, or not roughly, I know how far I moved in the y-axis, right? Up or down, north or south, okay? So add up all the x components to get the total x vector. Add up all the y components to get the total y of your overall vector, okay? Once you've got that, well, then what you have found is the x component and the y component of the resultant overall displacement, right? What you will have found is this thing's x component and its y component. So drawing it off to the side here, you'll have found these sides of this triangle, right? Again, you got the resultant x by adding this thing's x component to this thing's x component to this thing's x component. Like that, right? And same in the y-axis. This thing's y component plus this thing's y component plus this thing's y component gives us our resultant y displacement. So if we know the x and the y component of our resultant displacement, right, we have two sides. We can find this resultant displacement itself with the Pythagorean theorem, okay? So steps 3 and 4, we're finding the x and y components. Step 5, we're finding the resultant vector itself from its components, okay? And finally, if we've gotten this far, right, we know we can get its direction with some SOHCAHTOA, okay? So use SOHCAHTOA to finally find the direction of the resultant vector from the components we found in steps 3 and 4. So I often tell students what we're essentially trying to do here is build the triangle that represents our resultant vector. So if we're adding two vectors like this and we want to know the resultant, we know it looks something like that, right? That's the result of adding those two. And we can see that it has a y component and an x component. Now, where did its x component come from? Well, from adding the x component of this to the x component of this, right? Where did its y component come from? Adding the y component of d1 to the y component of d2, right? Because they, again, both have a y component and an x component, right? d1 is at an angle, so it has an x-ness and a y-ness to it. Same goes for d2. It's got an x component and it's got a y component. And so we can see that adding d1x and d2x is how we get our resultant x component, right? Overall, how far did we move in the x-axis? Well, this plus this, right? How far we moved in the x-axis during d1 plus how far we moved in the x-axis during d2. So drx is d1x plus d2x. And it's the same thing in the y-axis, right? We went that far in the y-axis for d1, and then we came back this far in the y-axis for d2, right? So add those two together, keeping in mind they have opposite signs, will give us the resultant y displacement, okay? And so that's what we're doing here. We're building this triangle one piece at a time, okay? We need to build that triangle. So we get the x and the y components by adding the x and y components of each vector, okay? And then once we have the x and the y components, we get the vector itself with the Pythagorean theorem. And finally, we can get the angle with some SOHCAHTOA. Okay, it is a lot, I know. This is for sure the most challenging thing you've seen so far in Physics 20. And honestly, most students, when they first encounter this, find it to be the most difficult part of the course. It's not going anywhere, but by the end of the course, you've done it quite a few times with different vectors, so you do start to get the hang of it, okay? So if it's a little challenging at first, don't get discouraged. That's normal, okay? Make sure you're reaching out for help as needed. It does take practice. It does take time. You can do it, okay? Let's get some practice putting all of our skills together now, and then we'll be done. Before we do, just going to take a look at a quick visual here to really drive home the point, okay? Say we have two vectors like this in 2 dimensions, right? We know that their sum looks something like that. And we also know that since they're off at an angle, each of them, right, they have components that look like that, right? There's their x components and their y components, okay? Their sum also has x components and y components. So to get the total x component of this sum vector here, right, how do we get that? Well, again, the resultant vector is the result of adding up all of the other vectors. And the same goes for its component. So its x component is the result of adding the x components of these other two vectors. So just focus in on the x components for now, and let's add those tip to tail, right, like that, okay? And notice that's just the exact length of our x component for our resultant vector, right? Adding those x components tip to tail down here, that just gives us the x component of our resultant vector. So the resultant x component is adding the x component of vectors 1 and vector 2. Okay, so now switch to thinking about the y components, right? Again, the y component of our resultant vector is just the result of adding the y components of these two vectors. So I'm going to take these, move them around, add the y components only tip to tail, and sure enough, look at that, right? That's where that thing's y component comes from. So all we're doing, like I said, is building this sum vector. We're going to find its x component by adding this thing's x component to this thing's x component. One side down. Okay, then we're going to find its y component by adding this thing's y component to this thing's y component. 2 sides down. Once we've got this thing's x and y components, we can find the vector itself with Pythagorean theorem, and finally its direction with SOHCAHTOA. So here is kind of a visual summary of the whole process, right? We want to know the resultant displacement, add up all the x components of each individual vector to get the resultant's x component, add up all the y components to get the resultant y component, Pythagorean for this, and finally SOHCAHTOA for its direction. Okay, now let's work through a guided example here. So we want to find the magnitude and direction of the resultant vector We're going to start with a guided example that breaks down the steps for you. Okay, that won't always be the case, of course, but these are the steps we follow every time. So you can always come back to this example and see, okay, here's the general process. So Tom walks 15 meters east, then 12 meters at 65 degrees east of north. Okay, so we know that we definitely want to draw our diagrams, and then we know we can only add x's to x's and y's to y's. Well, this has a combination of an x component and a y component, so we're going to need to find that component. Okay, so first things first, let's draw our vector addition diagram. Now, first he walks 15 meters east. I'm going to call that D1, okay? And actually, that one is entirely in the x-axis, so that's kind of nice, right? There's D1, 15 meters east. Now, D2 is a little more complicated. It's at 65 degrees east of north. So we can deal with that, right? I would like to just draw a little thing off to the side here. We know we're somewhere between north and east, right? D2 is pointed something like that. And how far exactly? Well, it's 65 degrees east of north, okay? So that means east of north, right? Here's north. We're going to go 65 degrees east of it. Sometimes students like to put a little plane there just to help themselves think about it. Yeah, if you want to do that, totally, right? So 65 degrees east of north. That's what D2 is going to look like roughly. Okay, and so for the resultant displacement, he ends up something like that, right? From where we started to where we finished. And that's the whole point of the question, is to figure out what that is. Now, again, we know we can't add these. In fact, right now we can't do anything with these numbers because they're not in the same axis, right? We can add x's to x's and we can add y's to y's. So we know we're going to need to find the x and y components of D2 before we can add the x to that, right? And get the y component. So let's just go ahead and do that right off the bat. So first things first, for that, let's just find our D2 components, okay? If D1 had x and y components, we'd have to do that too, but we got lucky here. D1 was all in the x-axis, so it's all x, no y, okay? That's easy. So for the D2 components, I like to avoid clutter, just redraw it, right? Let's just redraw D2 so we can focus in directly on it. And now we can kind of easily see, okay, so what's the y-ness of D2? Well, it looks something like that, right? There's D2's y component, and there is D2's x component, right? We're essentially finding the northness and the eastness of walking 12 meters, 65 degrees east of north, right? Okay, now again, I was being a bit strategic there. I chose to draw it this way because I already drew this and I knew that that was the angle I was given. If you happen to draw it the other way, so you did x then y, that's okay. You would just have to realize that, whoopsies, this angle is 65, so I have to figure out what this angle would be. In this case, it would be 25 degrees, and then you could draw your triangle and keep on going. Okay, so now I know that this is 65 degrees referenced to north there, and I can find my components. So I have the hypotenuse of this triangle. It's 12 meters, okay? To get the y component, I need the angle, I'm going to use the side adjacent to my angle. So adjacent hypotenuse, I'll use cosine to get the y component. And then opposite hypotenuse for the x component, I'll use sine. Okay, so I've just set up my two ratios there like we've been doing. Cos 65 is adjacent over hypotenuse. Sine of 65 is opposite over hypotenuse. Let's go ahead and solve both of these. Multiply by 12 here, multiply by 12 here as well, and we'll get our x and y components. Okay, so there we go, right? I figured out that D2y is that's how far we moved. In which direction? North, right. The y component is talking about the northness for this thing here, where we went east of north. And the x component is talking about the eastness. So how far did we go east during D2? And how far did we go north during D2? Okay, now again, can't emphasize enough. Notice I am not rounding these too much because I'm going to use those numbers over and over. I don't want to round so much that I change my final answer. Okay, so there we go. That's kind of like our setup, right? We've laid out our tools on the table. We're now ready to go ahead and start actually solving for stuff. So our goal here is to find this, right? To find the resultant displacement, dr. Okay, which is just the result of adding these two together. So we can find the x component of dr and its y component by separately adding up the x and y components of each vector. So in other words, drx is d1x plus d2x, right? dry is d1y, which is 0 here, plus d2y, which we've just found d2x and d2y. We have d1x and d1y. We're ready to go. But we are about to add vectors, so we want to be very careful that we make sure, right, we are keeping track of signs. So I'm going to call in the y-axis, I'm going to call north positive and south negative. In the x-axis, and in the x-axis, I'm going to make east positive and west negative. Okay, so here we go. We've got, again, there's our game plan, right? Find drx by adding up all the x components. So let's do that first. Then we'll do the same to find dry, but with y components. Truth be told, doesn't matter which one of these you find first. Essentially where we are here, right? Again, we're building this triangle. So right now we're going to find these sides by adding up all the x components and all the y components separately. So drx, always the same thing. It's just the sum of the x components of all the vectors you have. In this case, we have two vectors, right? d1 and d2. So add d1's x component to d2's x component. And in our case, d1x is actually just d1. d1 is entirely in the x-axis. It's all to the east. So we can just do positive 15 meters. d2x, well, we found that in our first step here to be this number, right? That's why we went and found it, so we could add it to the x component of d1. Since they're both to the east, I give them the same sign, in this case positive, to get that the total x displacement is 25.8757 meters, positive, so to the east, right? And we can pause there and check our work. Does that make sense? I mean, yeah, it does, right? If this was to the east, this was just even further to the east while also going north, but horizontally to the east, right? Yeah, makes sense that our resultant displacement overall in the x-axis was to the east. Now let's do the same thing for the resultant y, okay? So what we've done so far is find this side of the triangle. Now we got to find this side, but it's the same process. dry is d1y plus d2y, right? And in this case, d1y component is actually just 0 because this didn't take us north or south, right? So we can see here that our resultant y displacement is actually just going to be d2's y component. Now, this actually makes a ton of sense, doesn't it, right? Because what this is saying is overall, how far did they displace themselves to the north or south, right, in the y-axis? And what we've just said with our equation is, well, it's just going to be how far they displaced themselves during D2 north or south. And that makes a ton of sense because during D1, did they go north or south? No, right? They only went east, so they didn't change their y-axis displacement at all during D1. The only reason they're going to be north of where they started is because of the fact that during D2, they had a northward component to their displacement. So the physics is kind of speaking to us through the math here, right? That's a mathematical statement of what we already knew to be true. So there we go. The resultant y displacement is just D2's y component, which we already found up here. So there we go. We've now got the x and y components of this resultant displacement. At this point, if I haven't already, what I like to do is just simplify, just take dr and just draw dr. Just take it and think about that resultant vector because we can now kind of focus in and realize what we've found, right? We've found that dr has an x component of 25.8757 meters east, and it has a y component of 5.07142 meters north, right? And I like to redraw it here, just simplify it a bit so that, we don't get too cluttered on our original VAD and we can focus in on what we've done. We found this by adding up all the x components. We found this by adding up all the y components. Notice we've got two sides of a right angle triangle, right? We have its x and y components for dr. We can just use Pythagorean theorem to find dr and then get its direction with some SOHCAHTOA. Based on how I drew it, I'll probably find that angle. So let's get the magnitude, the size of dr by using Pythagorean theorem. We can see it's the hypotenuse of this triangle. So dr squared is going to equal drx squared plus dry squared. Okay, let's put in our values and solve. So squaring our x component, squaring our y component, adding and then square rooting, I got that the resultant displacement was 26.368 meters. Okay, that's how big it is. And all that's missing now for a vector is its direction. But again, look how much the diagrams help us, right? They're not just an annoying thing we make you draw. We get you to draw them because they help you work through the problem, right? And they help us follow your work through the problem. So now, using our diagram, it's pretty quick and easy to see that, well, if we want to know theta, we have opposite, we have adjacent. True, we do have hypotenuse, but again, there was one more calculation involved in getting that. So it's just a little safer to use these because if we mess this calculation up, then we'll also mess up our angle. So I usually just like to go with opposite and adjacent. Plus, we usually have them written down nice and easy to reference because we just found them in the previous step. So finally, let's get that angle and we will be done. We can see that the tan of theta is going to equal opposite. So opposite to that angle is our y component over adjacent. Adjacent is our x component. And therefore, theta is equal to the inverse tan, second tan on your calculator of that same ratio. Putting that into my calculator, I got 11 degrees. Okay, so now put it all together, significant digits, all that good stuff. We were given only 2 significant digits in the question, so our answer should be that the resultant displacement is 26 meters. And in this case, again, we want to think about that angle, but I would actually be safe to say just 11 degrees. Because again, that's actually what I mean here, right? If this is 0 and this is 90, looking at our diagram there, I really do mean just go 11 degrees. We could also say 11 degrees north of east. That would work here too. So maybe I'll say that. Let's say 11 degrees north of east. Okay, because again, over here on the diagram, this would be north, this would be east, and we are 11 degrees north of it. That's actually what we mean in this case. Okay, can we put all the steps together without being guided through them? The final example for this lesson. Let's go ahead and try it out. Okay, so a cat runs 5 meters south. I'm going to call that D1 south, so it's all in the y-axis. 3.8 meters west, D2, and hey, that's west, so it's all on the x-axis. And then, D3, a little more complicated. It's got components in both axes because it's at 25 degrees north of east. So let's start out with kind of our setup steps here, right? Where we're going to draw our VAD, our vector addition diagram, and then we know that we need to separate this into its x and y components so that we can add its x component to these things x components and its y component to these things y components. So here we go, VAD. So first it goes 5 meters south, then 3.8 meters west, so a little bit less than 5, that's D2. And finally, 27 meters at 25 degrees north of east. Okay, so again, before we draw that, let's just get our bearings. We know we're somewhere between north and east. Some students, and I think it's maybe a good idea if you're having a tough time with it, okay, just put a little thing there, right? You know that's north, you know that's east. We need to now point this 25 degrees north of east. So starting from there, right, we need to be 27 degrees north of east. So our vector's pointed something like that, and 27 is much bigger than those other two. So I'm going to draw it much bigger than those other two, right? So all we did was we went south, then we went west, then we went north of east, 25 degrees north of east to be specific. Whoops, I think I said 27 degrees earlier. Sorry, I was mixing up the magnitude and the direction. 25 degrees is that angle there. Okay, now again, we know we're going to need D3's components, so let's just do that before we go much further. And oops, I actually forgot the most important part of a VAD, right? The resultant. So roughly, we know that, okay, we started here, we ended up here. So our resultant displacement should look something like that, right? That's what we're predicting roughly, something like that, okay? All right, now let's get those D3 components. Again, I like to to simplify, let's just redraw D3 without all of the clutter, okay? We know that D3 has an x component and a y component, right? It's eastness and it's northness, okay? And this angle here, well, again, we know it's 25 degrees north of east. So reference to the horizontal, if this is east, we're 25 degrees north of it when we're facing in the direction of D3. So this is 25 degrees. Again, if you had drawn it this way, that would be okay. You would just have to do some math to figure out what that angle would be, okay? So this is 27 meters. We want to know these x and y components. Well, trigonometry will be our friend here, right? So sine of an angle is equal to opposite over hypotenuse. So with sine, I can find d3y. Cosine of an angle is adjacent over hypotenuse. So with cosine of 25, I can find d3's x component. So let's set up our ratios just like this, right? Opposite over hypotenuse, adjacent over hypotenuse. Multiply both sides by 27 and we'll have our components. Okay, so for the y component, I got this as its magnitude, right? And its direction is, well, to the north, right? So that's how far north we moved during D3, while at the same time in the x-axis, we were moving this far to the, you got it, to the east, okay? So there, now we've got all our components all separated. Do we need to do it for D1 and D2? I mean, sort of, but it's already done for us, right? This has already been separated into its y component and x component. It's just that the x component is 0. It's all y in the south direction, no x, right? Same idea here, but all x, no y. Okay, so again, just the reminder here, what we're trying to do is figure out dr, okay? What we're about to build is the triangle for dr, where we look at what is dr's x component, right? Normally we don't draw it on here because it gets too cluttered, but just to give you the visual. And what is dr's y component? Well, drx is going to be d1x plus d2x plus d3x. dry is going to be d1y plus d2y plus d3y. We have all of those x's and y's. We just need to add them to start building this triangle, getting these two sides. So let's go ahead and do that. Now, before I add anything, right, it's especially going to be important on this one because I do have things in opposite directions. Let's make sure we're being consistent. So in the x-axis, I'm going to call anything to the east positive, and therefore the opposite direction west, I will call that negative. And in the y-axis, let's call north positive, and therefore south negative. So now that we're going to find drx, I got to be really careful about my signs here. But the resultant x displacement will be d1's x component plus d2's x component plus d3's x component. That's all it ever is. The sum of all the x components gives you the resultant x component displacement. Now d1's x component, what is it? If we went 5 meters south, how far west or east did that take us? Right, 0. We're still just as far west or east, so that doesn't contribute to the resulting overall x displacement, right? But d2x, okay, now this took us west, right? So that's definitely, it's all x. In fact, d2x is just d2, okay? I defined west as negative, so I'm going to put that in as negative 3.8 meters. And then d3x, well, we just found that. It's this far to the east. So notice how important directions are, right? If I forgot that negative there, I would get the wrong answer. I have to remember that opposite vectors in opposite directions cancel each other out. Okay, so the total amount we displaced ourselves just in the x-axis, I'm getting positive 20.6703, which we know means it's to the east. Checking our work as we go, yeah, that makes sense, right? Because yeah, we did go west, but we went way further at an angle north of east, right? So sure, it was at an angle, but still, that's a long distance and it was to the east. So I'm not shocked that it canceled out how far we had gone west and then some to leave us somewhere to the east. Okay, now repeat with dry. Add up all the y components. But it's the same process. Add them all up to get our resultant y, okay? So d1's y component, well, it's all y component, but we have to remember south, so we're going to make that negative 5, okay? And d2's y component is actually just 0 because when you were moving to the west, 3.8 meters, you weren't going north or south. Your y displacement wasn't changing. D3's y component is to the north, so we'll make that positive. Let's put in our numbers. And so that's what I'm getting for the overall northness of our total displacement, okay? And I know it's north because it's positive. So again, just to kind of see the big picture here, and at this stage, I would do this either way, okay? What are we doing? We're trying to find dr. Well, here's what we've done, right? We knew dr from our diagram looked something like that, and therefore we knew it had an x component and a y component. And we've now found those components by adding up all the x components of every vector that went into making dr, right? We now know these two sides of the triangle. We know that side and we know that side. Well, with two sides of a right angle triangle, what can you find? You can find the third side using Pythagorean theorem. Very good. So let's get the magnitude of dr, okay, with Pythagorean theorem. So always hypotenuse squared equals this squared plus this squared. And therefore, the resultant displacement will be the square root of our components squared and then added together. Okay, so doing that and square rooting, I got that the resultant displacement's magnitude would be 21.64159 meters. That's how far, right? All we're missing now is which direction. And notice once again how helpful it is to have those diagrams along the way, right? Because now we can just go back to our diagram and say, okay, well, I know I need an angle to be specific about the direction. That angle will do just fine, right? So to get the angle now, we can just use trigonometry, right? I like to just go with these because they're written down nice and easy to reference, and there was one less calculation involved in getting them, so they feel a bit safer. So I have opposite and adjacent. To get this angle, TOA, I can use tan. And therefore, theta is the inverse tan of that same ratio, opposite over adjacent, giving me an angle of 17.2 degrees, okay? Now, always thinking carefully, remembering that we might have to place this, between north and east or between 0 and 360. But once again, in this case, actually, it worked out that I could just say that. I could get away with just saying 17 here, because if this is 0 and this is 90 and we go 17 degrees counterclockwise, we actually are saying the angle we mean, okay? Or, since we talked about north and east in the question, we can say north and east in our answer. So would we say 17 degrees north of east, or would we say 17 degrees east of north? You got it. It would be north of east, right? Here's east, and we can see we're 17 degrees north of east. Okay, so putting it all together until our final answer, to two significant digits, because that's what we were given in the question, we would say 22 meters at 17 degrees north of east. And there we go. Okay. And so I know it's a lot. I know there's multiple steps, right? I warned you that a lot of problems we'd solve in physics would take multiple steps, okay? But break it down into step-by-step process and keep your eye on the prize, right? Think about the big picture. What are we doing? We're ultimately just trying to build this triangle, right? In order to get this side, we add up all the x components, which means we might need to break some things down into their x components, like we did at the very beginning here, right? Do the same for the y components to get the total y. With the total x and with the total y, you can use Pythagorean to get the vector itself, and finally SOHCAHTOA for the direction. Okay, so it's always that same process. Takes a little time, definitely takes practice, okay? But good news, there is lots of practice ahead of you, okay? So we are finished with the notes and examples for this lesson. You are now good to go complete the rest of your practice problems. Make sure you are doing that again, right? Practice is so important, especially with these newer, more difficult concepts, okay? And as always, with any concept, but especially here where you might be starting to run into a little bit of difficulty, make sure you're reaching out for support, okay? That's why I'm here. I'm always happy to help, okay? So start out with this one. Okay, you'll notice you have two vectors there that each need to be separated into their x and y components, but it's the same process. Separate them, add the x's separately, add the y's separately, and then use Pythagorean with the totals to get the resultant itself. Okay, all right, we're done.